We're starting to go through the Hewlett-Packard 400D AC vacuum tube voltmeter. And in part one of this series, we just kind of looked through the interior of the meter to see how it looked, and we looked at the outside of the meter and were impressed with the condition that we found this meter in. In this video, I'm going to start going through and understanding the circuit and which variant of the circuit we have, and start testing the components to see how they've aged. And in future installments, we will replace the components that need replacing and figure out how to do some sort of a calibration on this so that it becomes an active and useful piece of bench equipment. So you can see here that I have disconnected some of the components from the circuit to some extent. Right, there's dangling wires and leads that I've disconnected, and I've done that just to kind of randomly check and see how leaky the capacitors are and whether or not these resistors are likely to have drifted out of their specified ranges. What have I done so far? Well, one thing I did was I replaced the fuse holder. So that's a new fuse assembly. The old one was very beat up and had pieces missing from it, and so just figured, well, that's easy to do, and I've got extras of those on hand, so I went ahead and did that. Before I start going through the various components, it seemed important to find, if I could, a schematic diagram for this instrument. So, how hard can that be? He said. I went to the internet and found a manual for this meter, or a variant of this meter, and I thought, well, it might not be exact, but let's see how good it is. So I started spot checking some bits of this. And the easiest bit that I started with was surrounding the meter itself. On this version, maybe I can zoom in here, there are two electrolytic capacitors. There are two capacitors here, and on each side of the bridge, and they're each 2 microfarad. And when I checked those, I found that in reality, and they were right over here on the other side, so in fact they are these two objects, which I've taken out of the circuit. I found that they were each 1 microfarad. Well, you know, sometimes manufacturers use what they had on hand, but you usually found that with lower quality pieces of bench gear, not a high-end Hewlett-Packard meter, high-end for the day. What else did I find that seemed suspicious? Well, another thing that was easy to check was this pilot light here. So this hangs off of one of the filament secondaries of the main supply transformer. And you see that it goes directly from one lead of the secondary to the bottom of a rectifier circuit. There should be nothing in between there. But let's turn that back around. When I did that, this is what I found. So let's go over here. So here is the pilot light. You see there's a brown wire and a gray wire. And if you follow that up, it goes right to here. One of them goes to here, and the other wire, when you trace it back, it goes back, in fact, to the secondary. But this goes to this resistor right here, and that's orange, orange, black. So that should be a 33 ohm resistor, and that was nowhere to be found on the schematic that I was easily able to locate on the internet. So what did I do? Well, I did a bit more careful searching and I found that Hewlett-Packard had published some service bulletins. One of the service bulletins I found had two schematics, and this bulletin concerned changing the input circuit from a capacitive input divider circuit to a resistive input divider circuit. And the principal issue there was on, in fact, the input circuit. So here's your input, and on this version of the input, it is cycled through, the input goes through a 0.01 microfarad capacitor into another RC network down here. That's with the capacitive input divider circuit, right? There we go. But for the resistive input circuit, it goes directly through, the input goes directly through a 47 ohm resistor into a 0.047 microfarad capacitor, right? And so that is the as far as I can tell, the final version of the meter, which was the resistive input divider circuit. On the capacitive input divider circuit, also notice there are 1 microfarad capacitors on the bridge, as there is on the capacitive, the resistive input divider circuit. Okay. There were some other distinctions between the different versions of the schematic, but just to cut to the chase, if we go down to the input jack here, zoom in a little bit more, you will see the telltale 47 ohm resistor hanging off the input and going to a 0.047 microfarad bumblebee capacitor. So I believe I have the definitive schematic for this, although there are some, at least one difference between the actual circuit and what I have found on the, what I believe to be the appropriate schematic, and I will show you that. Well, let's show you what I'm talking about first, and then I'll show you how it's different than the schematic. Down here around this tube, hanging off of pin 1, this is pin 1 right here. Okay, maybe I'll get a different pointer. This is pin 1 right here. It's not a very good pointer either. Okay, how about this? There we go. So this is pin 1. Pin 1 goes to a 47 something. I say something because I have trouble with colors and I don't immediately know what the multiplier band is, but it's 47 something ohm resistor, which goes to a tie block, a terminal block, and then there's a wire underneath it that that goes to components on the other side. And then there's a, what, this is a 10 something ohm resistor. It goes to another terminal. And if you look at that terminal, this terminal doesn't attach to anything else. It's just hanging in the breeze there. It doesn't go anywhere. That is to say, one end of this 10 something resistor goes to a tube, but the other end doesn't go to anywhere. And I think what happened was that if you look at the way this terminal block is constructed, the other terminal is connected to ground. So it seemed like there was a component missing that went from here to here. And I would bet you, donut anyway, that it was a capacitor, right? So if we go to the schematic, and if you look on the other side, it's not immediately clear which vacuum tube it is, but by process of elimination, I think it's V1, because you can see the labels on the other tubes. And if you look at pin 1, there should be a, we can see this here, pin 1, there's a 47 something, in fact it's a 470 ohm resistor right there. And there's also a 10 something, it's actually a 10K resistor there. And it flows through a 0.75 picofarad capacitor. All these capacitances are picofarads, or microfarad in the parlance of the day, except otherwise noted. And that's missing. So either that was a mistake at the factory, or this was a modification that was described in a future, or at least in another service bulletin. I suspect it was actually an accident. If you look at that terminal block, it's very clean, the missing pin. I should say the unused pin. And if there was no capacitor intended there, then why install the 10K resistor? So it's kind of interesting. The archaeology of these instruments sometimes is kind of neat. Okay, so enough of that. I'm reasonably confident that this is the resistive input divider circuit, and other spot checks suggest that this instrument, as it is wired, is consistent with that. Okay, so I mentioned in the first video that these red, or maybe they're pink capacitors, these tiny chief capacitors, are notorious for going bad, i.e. becoming leaky with age, as they are paper capacitors. But they're sealed, and I also noted that none of them looked like they were cracked or otherwise obviously damaged. So I disconnected a few of these, and you know, they will all be replaced, just period. They will all be replaced. But I was curious as to how leaky they were, or whether they were leaky at naught. On the online forums, it is the conventional wisdom that tiny chiefs all leak, and you know, I was probably wasting my time even testing them. But you know, that just seemed like something I had to do. So let me turn on my Heathkit capacitive leak tester, and the magic eye should be lighting up. There we go. And what I'm going to do, set that to mini lytic. I'm just going to test that one tiny chief and see what it says. So this reads 0.5 microfarad at 400 volts. So first of all, so that's on ×1. So let's just change this around and see what the value reads. And the value reads about 0.55 microfarad, which is pretty good. It's pretty good for this instrument. And if you test this capacitor with, you know, a DMM capacity tester, you'll get a similar reading. I've, you know, gone through and aligned this instrument so that it actually does pretty good. But I don't much care what the magnitude of the capacitance is. I'm more interested at this point in the leakage. So let's now put this onto leakage test. And remember, when the eye is open, there is no current passing through the capacitor. It's when the eye is closed that we have current passing through it and leakage. So what did I say? I said 400 volts is the rating. So there's 3, 6, no problem, 10, 15. The eye closes and then comes back open. 25, 50, 100. It's opening, a little bit of wavering there, but 150, opening back up. 200, it's 250, it's opening back up again. 300. See that kind of oscillation back and forth gives me a little bit of pause, but it eventually stops squinting and opens up. So 350, and there's 400. You see it starting to, it's not open as widely. Took a while to get up there, but it's open. It's not leaking horribly. In fact, that capacitor is probably perfectly fine for that circuit. That is not going to cause me to leave it in the circuit, but it's interesting that the capacitor did well. Just while we're at it, let me turn this around and bring this back into the shot here. So that was this capacitor here. Let's look at this side of the meter, and I took out I took off all the capacitors in the bridge circuit. So that was, if you'll recall, that was a large electrolytic capacitor, a 500 microfarad, but only 15 volt capacitor directly across the meter. Whoops, here we go. 500 microfarad electrolytic across the meter, and then 2 1 microfarad capacitors on either side of the bridge. So I took those out here. So these are the tiny chief. These are the 1 microfarad tiny chiefs, and this is the 500 microfarad 15 volt Mallory. So let's put the leads on the tiny chiefs here. Remember, they both tie together. And let's test the leakage of at least one of these. Probably go ahead and do both of them just to make the point. And so again, just for giggles, let's look at the bridge. Where's the bridge open up? The bridge opens up right there, and that's about 1 point. Sorry, about, yeah, 1 point, maybe 2, 1.1, 1.2 microfarad, completely reasonable value. And now these are also 400 volt rated capacitors, so opens up, it's fine, doing good. So at 200 volts, it's really squinting. It eventually opens up, but again, that, kind of blinking is worrisome. That's at 200 volts. 250 volts, yeah, we've got issues there. And 300 is just completely leaky. So that's that. Discharge that there. And let's look at the other capacitor now. That's the second one in the bridge circuit, the meter circuit. Let's just see what that one reads. Just about the same as the other capacitor in terms of capacitance, but now let's look at the leakage. So opening up at the low voltage, fine, no leakage. It's slowly opening up at 150 volts. There's 250. You're seeing a little bit of craziness there. It's squinting and kind of blinking. 350. There's, the eye is not opening up widely at all. And if we go to 400, you'll see that it is absolutely leaking. So it would seem that the conventional wisdom is in fact correct, that tiny chiefs have got to go. Okay. There's one other capacitor that I do want to test. And that is, I should say that the Mallory, it is literally not even worth the time checking that. So there is one other capacitor that I do want to take a short little gander at. And that is in the rectifier, one of the rectifier circuits. There are these insanely large electrolytics. And by large, I don't mean physically large, I mean electrically large. 1500 microfarad filter capacitors. Now, they're very large, but they're rated at 15 volts. So just kind of curious to see how those measure up. And those are the capacitors in this can. This is the bottom side of a can. And I just lifted one lead off of one of the 1500 microfarad capacitors there to set up a leakage test. So we're going to hook one, right, the negative lead to the ground, and no, I did not make a mistake there. That is a capacitor lead, but that capacitor lead is in fact tied to ground on the next pin there. So I'm going to put the negative lead there and the positive lead over to the opened up, not electrically, I mean physically open capacitor wire. Okay, and let's just go back over to here. And since this will only measure up to 50 microfarad for the bridge, I'm just going to use the leakage function here. And just curious to see how this is aged. So 3 electrolytic. Okay, so 3 volts is fine, 6 volts is fine, 10 volts is fine, and at 15 volts we are not leaking. Let me just discharge that and put 15 volts on it again. So this appears to be completely fine, which is good because I don't have any 1500 microfarad capacitors in my stock. Okay. What else as this video becomes longer? As I said before, the Bumblebee capacitors, like here's one there, there's a whole bunch on the other side, here's one. Those will all go, and I think most all of them are 0.047 microfarads, but those will all go because they are even more notorious than the tiny chiefs for leaking. Let's very quickly just check a couple of these capacitors that I've lifted up, and for no very good reason, let's just start with this one here. So what we're going to do is put this on, okay, and let's just look at this capacitor, I'm sorry, resistor. All right, so this is a red, yellow, red resistor. And so that would be 4 times 10 to the 2, so 24 times 100. So this is a 2.4 kilo ohm resistor. And you see we're not reading much out of the ballpark on that. But what, is this intolerance? So the other band on this resistor is gold. And so gold means plus or minus 5%. So what's 5% of 2400? That's 0.05 times, that's 5 times 24, which would be 120. Yes, 120. So that means that this resistor is in tolerance if it is between, what, 2280? Yeah, 2280 and 2520. You see that this is less than 2520. This is, in fact, intolerance. So that's interesting. Let's look at this resistor here. This is orange, black. So that is what, 33 ohms, and it's silver. Silver's what? Silver's 10%. So that would be 33 plus or minus, call it 3 ohms. So that would be intolerance if this were under 38 ohms, right? 33, 6, I'm sorry, 30, 10% of 33 is 3.3, so 33 ohms plus 3 ohms would be 36 ohms. So this is also in tolerance in this position. So the resistors are not obviously bad. Now I've checked 2 resistors out of, probably 80 resistors or 100 resistors in this lot. You have to do better than that. But the spot checks suggest that, maybe this was stored in a well-controlled environment, a dry environment, say, and the resistors haven't obviously changed, drifted is the word I'm looking for. Okay, let's see. There is one other thing that I noticed that I want to point out, and that has to do with the the capacitor cans. So that's, these. They're my dogs warning us, if you can hear them, that you should always be suspicious of cans that are 60-ish years old, and they are emphatically, you can't argue with the dogs. And what I want to show you here is that on this capacitor, which is the 1500 microfarad capacitors that we just looked at, they look fine. There's nothing coming out here. If you can see, there's nothing coming out, spewing out from the pins. But if you look up here at this one, I don't know if you can see it. It's kind of hard for me to tell if you can see that or not. But there, right there is a glob of something that has spewed out. Sorry if I could move my hand so you can see. Right there is a glob of something that has spewed out, and also right there, and that's electrolyte that has leaked out and dried. Just right there and right there. Okay, and I won't try to show with a close-up because I'm not sure that I've done a good job of setting up the shot with the lighting and stuff, but in this can as well, there's signs of electrolyte that has leaked out. And I don't see any in this can, but certainly in this one right here and in this one right there, there has been electrolyte leakage. So those, I believe, were mostly sets of 20 microfarad capacitors. Those are quite easy to replace. In fact, I have a bunch of those on hand, so those will be replaced as well. Okay, we're now approaching half an hour, and that's probably a good place to stop. I have cleaned this up a little bit. There's a lot more cleaning to do, but I think this is coming along. I will probably go ahead and stop here and go through and replace the capacitors begin replacing the capacitors and spot checking more resistors and doing those sorts of things, order the parts that I need to order, and we'll come back and as this is a work in progress, check back in and show how things are going and talk about anything that I've discovered that seem noteworthy. Okay, so that's video number 2 in the series on the Hewlett-Packard 400D AC vacuum tube voltmeter. I hope this has been interesting and even useful if you're going through a similar restoration. If you like it, please leave a thumbs up below, and if you don't subscribe to the channel, please consider doing so. As always, thanks for watching.